This is the second video from section 6.1. And so here we're going to finish example 157. And so our function that's written in the notes is z is x times e to the xy. I have written this as z equals fxy is equal to x times e to the xy, so I can use function notation for the partial derivatives. So we start by calculating the partial derivative with respect to x, which requires the product rule. So if we look at this as x times e to the xy, the partial derivative with respect to x of x is 1. And so we have 1 times e to the xy. And then we have x times the partial derivative of e to the xy with respect to x. So this is an exponential function. So we just have e to the xy times the derivative of the exponent, or rather the partial derivative with respect to x of the exponent, which is y. The partial derivative with respect to y, we regard x as a constant, and so essentially we have constant times e to the constant times y. And so we take the partial derivative with respect to y of e to the xy. So we have e to the xy times x, and so we have x times x, which is x squared. Evaluate the partial derivative with respect to x at the point 1, 0. Evaluate the partial derivative with respect to y at the point 1, 0. Sometimes we have to calculate the function itself at the point 1, 0, but that was given to us already as 1. And so we have z minus the z coordinate is equal to the partial derivative with respect to x times x minus the x coordinate plus the partial derivative with respect to y times y minus the y coordinate. This plane simplifies nicely to z is equal to x plus y. Now, we're going to generalize this concept of a linear function. And so we have a function f from Rn into R. We have c as a point in Rn, and f is nice. All the partial derivatives of f are continuous at c. That's what we mean by nice. Now, if f is a function of only two variables, then really what we're doing is we're writing the tangent plane here. But because f is a function of a lot of variables, we can't necessarily call this a plane. It might exist, it's a plane if it exists in 3 space, right? If it has 3 variables and it's a linear function, it's a plane. If it has 5 variables, we can't call it a plane. It's hard to imagine. But it's a linear function of 5 variables. But we get that function in pretty much the same way we do as the tangent plane. We take z minus f of c. So c is a point in Rn. Then we have the partial derivative with respect to the first variable times, well, the first coordinate of x minus the first coordinate of c, down to the partial derivative with respect to the last variable of f, evaluated at c, and then the last coordinate of x minus the last coordinate of c. It's just a generalization of what we did with the last 2 examples. We just have more, we have a higher dimension for our variable and for our point. And so we take this and we write this in function notation, and this is the linearization or the linear approximation of f at c. This is a linear function. Why are we interested in that? Because L of x is approximately f of x for x close to c. And just like in Calc 1, the closer x is to c, the better of an approximation this is. In Calc 1, close simply meant the absolute value of x minus c was small. Here we have to use the Euclidean metric. Now, also recall from Calc 1 what happened. We had the equation of the tangent line, y minus the y coordinate, is equal to the slope times x minus the x coordinate. The y coordinate is f of c, the slope is f prime of c. Then we took that tangent line and we wrote it in function notation as a linear function, and that was the linearization of f at c. And the idea is, I'm out of room here, But L of x down here is approximately equal to f of x, just like it was in Calc 1. So L of x is approximately f of x. So that's why it's called a linear approximation. The closer x is to c, the better the approximation.